Hello, this is Dr. KSNV Prasad, Assistant Professor, Department of Chemical Engineering, B.V. Raju Institute of Technology, Narsapur. In this video, we are going to discuss about the fundamentals of nanotechnology. Fundamentals of nanotechnology is open elective course which is designed for non-chemical engineering students especially, because chemical engineering students, they study it as a main course. And coming to the case of nanotechnology, nanotechnology is one of the emerging courses which is having ample scope and ample opportunities for the students who excel in nanotechnology. So that is why I advise all the students to be well versed with the fundamentals of nanotechnology, which can help you people to excel if you take nanotechnology as research field in future, because in nanotechnology we have ample opportunities for research, and as well as nanotechnology is a multidisciplinary course. Hence, I advise the students to be well versed with the basics of nanotechnology. In this class, we will discuss about the background to nanotechnology. Coming to the case of syllabus that is mentioned for the open elective students, in Unit 1, we are going to study the background to nanotechnology. In background to nanotechnology, we discuss the basics like the scientific revolution, molecular and atomic size, emergence of nanotechnology, challenges in nanotechnology, and carbon age. All the fundamentals are being covered, very basic fundamentals are being covered in Unit 1. And coming to the case of Unit 2, we discuss about nucleation, that is macroscopic to microscopic crystals and nanocrystals, top-down and bottom-up approaches, self-assembly process, grain boundary volume in nanocrystals, defects in nanocrystals, surface effects on the properties. And coming to the case of Unit 3, we discuss about the nanomaterials and their properties. Here we will discuss about the types of nanostructures, that is one-dimensional, two-dimensional, three-dimensional nanostructured materials, quantum dots, quantum wires, quantum sheet structures. And coming to the case of Unit 4, we will discuss about carbon nanotubes, metals, metal oxides, semiconductors, ceramics and composites, biological systems, DNA, RNA, lipids, size-dependent properties, mechanical, physical and chemical properties. And finally, coming to the case of Unit 5, we will discuss about the applications of nanotechnology. Molecular electronics and nanoelectronics, quantum electronic devices, carbon nanotube-based transistor and field emission display. Biological applications and biochemical sensors, along with membrane-based water purification techniques. Coming to the case of textbooks. Textbook of Nanoscience and Nanotechnology by B.S. Murthy, P. Shankar, Baldev Ras, B.B. Rath and James Munday. As well as Nanotechnology, Basic Science and Emerging Technologies by M. Wilson, K. Kannan-Gara, G. Smith, M. Simmons, B. Raghus. And these are the prescribed textbooks. And coming to the case of references, the chemistry of nanomaterials, nanostructures and nanomaterials, Hari Singh Nalwa and Hari Singh Nalwa's Handbook of Nanostructured Materials and Nanotechnology, Nanofabrication towards Biomedical Applications. So these four are the reference materials. Now, coming to the case of background to nanotechnology, let us first discuss about the definition of nanoscience and nanotechnology. Even though nanoscience and nanotechnology look one and the same, but there is a slight difference between these two words. The prefix nano is referred to a Greek prefix meaning dwarf or something very small and depicts 1,000 millionth of a meter, that is 10 to the power of minus 9 meters. We should distinguish between nanoscience and nanotechnology. Nanoscience is the study of structures and molecules on the scales of nanometers ranging between 1 to 100 nanometers. And the technology that utilizes it in practical applications such as devices, etc., is called nanotechnology. So that is the difference between nanoscience and nanotechnology. As a comparison, one must realize that a single human hair is 60,000 nanometer thickness and the DNA double helix has a radius of 1 nanometer. The development of nanoscience can be traced to the time of Greeks and Democritus in the 5th century BC. When scientists considered the question of whether matter is continuous and thus infinitely divisible into smaller pieces or composed of small, indivisible, and indestructible particles, which scientists now call atoms. In these diagrams, we can be able to analyze how nanomaterials are different from the materials that we see with our naked eye. For example, the large raindrop is around 1,000 times bigger than a bacterium, which is in turn 1,000 times bigger a DNA. A DNA is 2.5 nanometer in diameter. Similarly, a single-walled carbon nanotube having 1 nanometer diameter is 1 lakh times bigger than the strand of hair, which in turn is 1 lakh times smaller than the house of 10 meter wide. Coming to the case of a nanoparticle of 4 nanometer diameter, if it is 10 lakh times enhanced, it will turn the size of an ant. Similarly, if this ant is 10 lakh times, the size is improved and it will convert into an Indianapolis motor speedway. Carbon nanotube buckyball is of 1 nanometer diameter, DNA is of 2 nanometer diameter, bacteria 0.5 to 2 micrometer, hair 60 micrometer, atom 0.1 nanometer, quantum dots 1 to 5 nanometer, viruses 10 to 150 nanometer, red blood cells 9 micrometer and neuron 200 micrometer. So these diagrams might have given an insight into the concept of nanotechnology. That means how small the nanoparticles are. Definitions of nanoscience and nanotechnology. Nanotechnology is one of the most promising technologies of the 21st century. It is the ability to convert the nanoscience theory to useful applications by observing, measuring, manipulating, assembling, controlling, and manufacturing matter at the nanometer scale. The National Nanotechnology Initiative in the United States defined nanotechnology as a science, engineering, and technology conducted at the nanoscale, that is 1 to 100 nanometer, where unique phenomena enable novel applications in a wide range of fields from chemistry, physics, and biology to medicine, engineering, and electronics. So, by this definition, we can clearly understand how nanotechnology is entering into various fields and how this nanotechnology can be employed by various fields for the development of various products which can be beneficial to mankind. Especially nowadays, nanotechnology is widely used in medicine. This definition suggests the presence of two conditions for nanotechnology. The first is an issue of scale. Nanotechnology is concerned to use structures by controlling their shape and size at the nanometer scale. The second issue has to do with novelty. Nanotechnology must deal with small things in a way that takes advantage of some properties because of the nanoscale. We should distinguish between nanoscience and nanotechnology. Nanoscience is a convergence of physics, material science, and biology, which deals with the manipulation of materials at atomic and molecular scales, while nanotechnology is the ability to observe, measure, manipulate, assemble, control, and manufacture matter at the nanometer scale. There are some reports available which provided the history of nanoscience and technology, but no report is available which summarizes the nanoscience and technology from the beginning to that era with progressive events. Therefore, it is of the utmost requirements to summarize main events in nanoscience and technology to completely understand their development in this field. Coming to the case of the imaginative pioneers of nanotechnology, the history of the background beyond the evolution of the science of nanotechnology, the main person who is credited as the father of nanotechnology is Richard Feynman. The American physicist and Nobel Prize laureate Richard Feynman introduced the concept of nanotechnology in 1959. During the annual meeting of the American Physical Society, Feynman presented a lecture titled "There is Plenty of Room at the Bottom" at the California Institute of Technology. In this lecture, Feynman made the hypothesis, why can't we write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin? And described a vision of using machines to construct smaller machines and down to molecular level. This new idea demonstrated that Feynman's hypotheses have been proven correct, and for these reasons he is considered as the father of modern nanotechnology. After 15 years, Norio Taguchi, a Japanese scientist, was the first to use and define the term nanotechnology in 1974. As nanotechnology mainly consists of the processing of separation, consolidation, and deformation of materials by one atom or one molecule. After Feynman has discovered this new field of research, catching the interest of many scientists, two approaches have been developed describing the different possibilities for the synthesis of nanostructures. These manufacturing approaches fall under two categories, top-down and bottom-up approaches, which differ in degree of quality, speed, and cost. The top-down approach is essentially the breaking down of bulk material to get nano-sized particles, as the name suggests. This can be achieved by using advanced techniques such as precision engineering and lithography, which have been developed and optimized by industry during the recent decades. Precision engineering supports the majority of the microelectronics industry during the entire production process, and the high performance can be achieved through the use of a combination of improvements. These include the use of advanced nanostructures based on the diamond or cubic boron nitride and sensors for size control combined with numerical control and advanced servo drive technologies. Lithography involves the patterning of a surface through exposure to light, ions, or electrons, and the deposition of material onto that surface to produce the desired material. The bottom-up approach refers to the building up of nanostructures from the bottom, atom by atom or molecule by molecule by physical and chemical methods which are in a nanoscale range, that is 1 to 100 nanometer, using a controlled manipulation of self-assembly of atoms and molecules. Chemical synthesis is a method of producing rough materials which can be used either directly in product in their bulk disordered form or as the building blocks of more advanced ordered materials. Self-assembly is a bottom-up approach in which atoms or molecules organize themselves into ordered nanostructures by chemical physical interactions between them. Positional assembly is the only technique in which single atoms, molecules or cluster can be positioned freely one by one. The general concept of top-down and bottom-up and different methods adopted to synthesize nanoparticles by using these techniques are summarized in the following figure. In 1986, K. Eric Drexler published the first book on nanotechnology, Engines of Creation, the Coming Era of Nanotechnology, which led to the theory of molecular engineering becoming more popular. Drexler described the build-up of complex machines from individual atoms, which can independently manipulate molecules and atoms, thereby produces self-assembly nanostructures. Later on, in 1991, Drexler, Peterson, and Pergamit published another book entitled Unbounding the Future, the Nanotechnology Revolution, in which they use the terms nanobots or assemblers for nanoprocessors and in medicine applications, and then the famous term nanomedicine was used for the first time after that. So, this picture shows the top-down as well as bottom-up approaches and the various techniques involved in it. In the top-down approaches, the bulk material is converted into nanoparticles by various techniques like mechanical processes, thermal processes, optical processes, sputtering and chemical etching. And coming to the case of bottom-up approaches, the atoms or molecules are combined together to form the nanoparticles by various methods like vapor deposition, sol gel method, chemical or electrochemical methods, bioreduction, atomic or molecular condensation. And coming to the case of the history of nanotechnology, nanoparticles and structures have been used by the humans way back in the 4th century AD by the Romans, which demonstrated one of the most interesting examples of nanotechnology in the ancient world. The Lycurgus cup from the British Museum collection represents one of the most outstanding achievements in ancient glass industry. It is the oldest famous example of dichroic glass. Dichroic glass describes two different types of glasses which change color in certain lighting conditions. This means that the cup have two different colors. The glass appears green in direct light and red purple when light shines through the glass. So, this is the picture where two different colors of glass are observed. In 1990, the scientists analyzed the cup using a transmission electron microscopy to explain the phenomenon of dichroism. The observed dichroism is due to the presence of nanoparticles with 50 to 100 nanometer diameter. X-ray analysis showed that these nanoparticles are silver-gold alloy with a ratio of about 7:3. That is 7 parts of silver and 3 parts of gold, containing in addition about 10% copper dispersed in a glass matrix. The gold nanoparticles produce a red color as a result of light absorption at approximately 520 nanometer. The red-purple color is due to the absorption by the bigger particles, while the green color is attributed to the light scattering by the colloidal dispersions of silver nanoparticles with a size greater than 40 nanometer. The Lycurgus cup is recognized as one of the oldest synthetic nanomaterials. A similar effect is seen in late medieval church windows, shining numerous red and yellow colors due to the fusion of silver and gold nanoparticles into the glass. The following figure shows an example of the effects of these nanoparticles with different sizes to the stained glass windows. So the gold particles in glass, if their size is 25 nanometer and the color reflected is red, and if the size is around 50 nanometer, the color reflected is green, and if the size is 100 nanometer, the color reflected is yellow. Coming to the case of silver particles, if the size is 100 nanometers and the shape is sphere, the color reflected is yellow, and if the size is 40 nanometer and the shape is sphere, the color reflected is blue. If the size is 100 nanometer and the shape is of prism, not sphere, here the color reflected is orange in case of gold nanoparticles of size 100 nanometer. During the 9th to 17th centuries, glowing, glittering, luster ceramic glazes used in the Islamic world and later in Europe contained silver or copper or other nanoparticles. The Italians also employed nanoparticles in creating Renaissance pottery during the 16th century. They were influenced by Ottoman techniques during the 13th to 18th centuries to produce Damascus saber blades. Cementite nanowires and carbon nanotubes were used to provide strength, resilience, and the ability to hold a keen edge. These colors and materials properties were produced intentionally for hundreds of years. Medieval artists and forgers, however, did not know the cause of these surprising effects. In 1857, Michael Faraday studied the preparation and properties of colloidal suspensions of ruby gold. Their unique optical and electronic properties make them some of the most interesting nanoparticles. Faraday demonstrated how gold nanoparticles produce different colored solutions under certain lighting conditions. The progression in nanotechnology due to the blessing of nanoscience are summarized in the following figure. So, 4th century AD, colored glass by Romans, British Museum Lycurgus, medieval church windows, 9th to 17th centuries in Islamic world luster, 16th century Italian Renaissance pottery, 13th to 18th century Damascus, 1857 by Michael Faraday ruby, 1879 CRO, 1895 XRD, 1928 Raman, 1937 SEM, 1938 TEM, 1969 XPS, 1981 STM, 1982 AFM by IBM. So this is the chronological order of history in nanotechnology. There was a progress in nanotechnology since the early ideas of Feynman until 1981, when the physicist Gerd Binning and Heinrich Roher invented a new type of microscope at IBM Zurich Research Laboratory, the Scanning Tunneling Microscope, STM. The STM uses a sharp tip that moves so close to a conductive surface that the electron wave functions of the atoms in the tip overlap with the surface atom wave functions. When the voltage is applied, electrons tunnel through the vacuum gap from the atom of the tip into the surface, or vice versa. In 1983, the group published the first STM image of silicon 7 by 7 reconstructed surface, which nowadays can be routinely imaged as shown in the following figure. So this is 7 by 7 STM image of silicon. A few years later, in 1990, Don Eigler of IBM in Almaden and his colleagues used a STM to manipulate 35 individual xenon atoms on a nickel surface and formed the letters of IBM logo. The STM was invented to image surfaces at the atomic scale and has been used as a tool with which atoms and molecules can be manipulated to create structures. The tunneling current can be used to selectively break or induce chemical bonds. In 1986, Binning and Roher received the Nobel Prize in Physics for their design of the STM. This invention led to the development of the atomic force microscope, that is AFM, and scanning probe microscopes, that is SPM. which are the instruments of choice for nanotechnology researchers today. At the same time, in 1985, Robert Curl, Harold Kroto, and Richard Smalley discovered that carbon can also exist in the form of very stable spheres, that is, the fullerenes or buckyballs. The carbon balls with a chemical formula C60 or C70 are formed when graphite is evaporated in an inert atmosphere. A new carbon chemistry has been developed, and it is possible to enclose metal atoms and create new organic compounds. A few years later, in 1991, Ijima et al. Observed of holographic tubes or carbon nanotubes by TEM, that is transmission electron microscopy, which form another member of the fullerene family. The strength and flexibility of carbon nanotubes make them potentially useful for many nanotechnological applications. Currently, carbon nanotubes are used as composite fibers in polymers and beton to improve the mechanical, thermal, and electrical properties of the bulk product. They also have the potential applications as field emitters, energy storage materials, catalysis, and molecular electronic components. So, the figure A represents the C60 or C70 atom, that is the buckyball, and the figure B represents is carbon nanotube. In 2004, a new class of carbon nanomaterials called carbon dots with a size below 10 nanometer was discovered accidentally by Xu et al. During the purification of single-walled carbon nanotubes. C dots with interesting properties have gradually become a rising star as a new nanocarbon material member due to their benign, abundant, and inexpensive nature. Possessing such superior properties as low toxicity and good biocompatibility renders C dots favorable materials for applications in bioimaging, biosensor, and drug delivery. Based on their excellent optical and electronic properties, C dots can also offer exciting opportunities for catalysts, energy conversion, photovoltaic devices, and nanoprobes for sensitive ion detection. After the discovery of graphene in 2004, carbon-based materials became the backbone of almost every field of science and engineering. In the meantime, nanoscience progressed in other fields of science like computer science, bioengineering, and other branches of engineering. Nanoscience and technology progressed in computer science to decrease the size of a normal computer from a room size to a highly efficient mobile laptops. Thus, nanotechnology played a crucial role in the advancement of technologies as far as computer science engineering is concerned. Electrical engineers progressed to design the complex electrical circuits down to nanoscale level. Also, many advances are noticed in smartphone technologies and other modern electronic devices for daily uses. So, like that, this nanotechnology finds its applications in various branches of engineering like electronics and communications, electrical and electronics engineering. At the beginning of the 21st century, there was an increased interest in the nanoscience and nanotechnology fields. In the United States, Feynman's concept of manipulation of the matter at the atomic level played an important role in shaping national science priorities. During a speech at Caltech on 21st Jan 2000, the US President Mr. Bill Clinton advocated for the funding of research in the field of nanotechnology. 3 years later, US President Mr. George W. Bush signed into law the 21st Century Nanotechnology Research and Development Act. The legislation made nanotechnology research a national priority and created a National Technology Initiative of the United States. Recently, a number of studies highlighted the huge potential that nanotechnologies play in biomedicine for the diagnosis and therapy of many human diseases. In this regard, bio-nanotechnology is considered by many experts as one of the most intriguing field of applications of nanotechnology. During the recent decades, the applications of nanotechnology in many biology-related areas such as diagnosis, drug delivery, and molecular imaging are being intensively researched and offered excellent results. Remarkably, a plethora of medical-related products containing nanomaterials are currently on the market of US. Examples of nanopharmaceuticals include nanomaterials for drug delivery and regenerative medicine, as well as nanoparticles with antibacterial activities or functional nanostructures used for biomarker detection like nanobiochips, nanoelectrodes, or nanobiosensors. One of the most important applications of nanotechnology to molecular biology has been related to nucleic acids. In 2006, Paul Rothemund developed the scaffold DNA origami by enhancing the complexity and size of self-assembled DNA structures in a one-pot reaction. The conceptual foundation of DNA technology was first laid out by Nadrian Seaman in 1982. It is possible to generate sequences of oligomeric nucleic acids which will preferentially associate to form migrationally immobile junctions rather than linear duplexes as they usually do. DNA technology has already become an interdisciplinary research area, with researchers from physics, chemistry, material science, computer science, and medicine coming together to find solutions for future challenges in nanotechnology. Notably, years of extensive studies made possible to use DNA and other biopolymers directly in array technologies for sensing and diagnostic applications. Remarkable progresses have been also made in the field of nano-oncology by improving the efficacy of traditional chemotherapy drugs for a plethora of aggressive human cancers. These advances have been achieved by targeting the tumor sites with several functional molecules, including nanoparticles, antibodies, and cytotoxic agents. In this context, many studies showed that nanomaterials can be employed itself or to deliver therapeutic molecules to modulate essential biological processes like autophagy, metabolism, or oxidative stress exerting anti-cancer activities. Hence, nano-oncology is a very attractive application of nanoscience and allows for the improvement of tumor response rates in addition to a significant reduction of the systematic toxicity associated with current chemotherapy treatments. Nanotechnology has been used to improve the environment and to produce more efficient and cost-effective technology, such as generating less pollution during the manufacture of materials, producing solar cells that generate electricity at a competitive cost, cleaning up organic chemicals polluting the groundwater, and cleaning volatile organic compounds from the air. However, the applications of computational approaches to nanomedicine is yet underdeveloped and is an exigent area of research. The need for computational applications at the nanoscale has given rise to the field of nanoinformatics. Powerful machine learning algorithms and predictive analytics can considerably facilitate the design of more efficient nanocarriers. Such algorithms provide predictive knowledge on future data have been mainly applied for predicting cellular uptake activity and cytotoxicity of nanoparticles. Data mining, network analysis, quantitative structure property relationship, quantitative structure activity relationship, and ADMET, that is adsorption, distribution, metabolism, excretion, and toxicity predictors are some of the other prominent property evaluations being carried out in nanoinformatics. Nanoinformatics has provided a major supplementary platform for nanoparticle design and analysis to overcome such in vitro barriers. Nanoinformatics exclusively deals with the assembling, sharing, envisaging, modeling, and evaluation of significant nanoscale level data and information. Nanoinformatics also facilitates chemotherapy by improving the nanomodeling of the tumor cells and aids detection of the drug-resistant tumors easily. Hyperthemia-based targeted drug delivery and gene therapy approaches are the latest nanoinformatics techniques proven to treat cancer with least side effects. And this is the summary of the evaluation of timeline of nanoscience and technology. 4th century, Lycurgus cup, 500 to 1400 AD, cathedrals, 1450 to 1600, that is Derrida pottery, 1857, Michael Faraday, synthesis of colloidal ruby gold nanoparticles, 1908, light scattering nanoparticles, 1928, near field optical microscope, 1931, TEM, 1936, field electron microscope, 1947, discovery of semiconductor transistor, 1951, invention of field ion microscope. This is the first to see the atoms on the surface. 1953, discovery of DNA by James Watson and Francis Crick. 1956, molecular engineering. 1958, electron tunneling. 1959, Richard Feynman, there is a plenty of room at the bottom. 1960, zeolites and catalysis. 1963, invention of ferrofluids. 1965, Moore's law. 1970, predicted the existence of C60 in the form of icosahedron. 1974, nanotechnology word is coined by Norio Tanguchi. 1974, molecular electronics. 1977, Raman spectroscopy. 1988, self-assembly monolayers. 1981, STMs. 1981, quantum dots. 1981 itself, molecular engineering. 1982, development of concept of DNA nanotechnology. 1983, discovery of colloidal quantum dots. 1985, discovery of Buckminster fullerenes, that is C60. 1960, 86 AFM. 1987, SET transistor. 1990s, arranged of individual xenon atoms to form the letters IBM. 1991, discovery of multi-wall carbon nanotubes. 1992, discovery of mesoporous silica. 1993, discovery of single-wall carbon nanotubes. 1996, DNA plus gold colloids. 1997, first nanotechnology company founded, that is Zivex. 1998, creation of a transistor using carbon nanotubes. 1999, DPN, 2000, FCL, 2000 itself, NNI, 2001, molecular nanomachines, molecular motors with nano scale, 2002, carbon nanotubes functionalized with DNA, 2003, US President George W. Bush signed into the law the 21st Century Nanotechnology Research and Development Act. 2003, development of gold nanoshells. 2004, discovery of graphene. 2004 itself, discovery of fluorescent carbon dots. 2005, nano car with turning buckyball wheels. 2006, DNA origami. 2007, artificial molecular machines. 2008, new Nobel Prize in Chemistry to Osamu Shimomura, Martin Shalfie, and Roger Y. Sipin for the discovery and development of GFP. 2009, DNA structure fold into three-dimensional rhombohedral crystals. 2010, development of an ultra-fast lithography to create 3D nanoscale textured surface. 2011, STM describes electronic and mechanical properties of individual molecules and polymer chains. 2016, Nobel Prize in Chemistry to Jean-Pierre Savez, Sir J. Franzer Stoddart and Bernard L. Feringa for the design and synthesis of molecular machines, 2017 Nobel Prize in Physics, 2017 for gravitational waves, 2018 world's smallest tic-tac-toe game board made with DNA, and 2018 shrinking objects to the nanoscale. So these are the evaluation of timescales of nanotechnology right from initial days to till recently. So this picture describes the entry of nanotechnology into various fields like chemistry, computer science, biology, and physics. So thus, this particular video might have given you an insight of nanotechnology. It's how it is diversified into various fields of engineering as well as science, and how this nanotechnology field has changed the advances in technology, etc. So with this, we come to the end of this video. And in the coming up video, we will discuss further into the basics of nanotechnology. With this, we conclude. Have a good day. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.